Hello, welcome to this lecture video. In this video, I am going to explain dielectric materials which comes under module 5 of engineering physics prescribed by VTU. Here I am going to discuss the following points, that is dielectric materials, polar and non-polar dielectrics, polarization, different polarization mechanisms, internal fields in a dielectric material. First, I am going to discuss about what are dielectric materials. So, in dielectric materials, the definition is the substances that do not conduct electric current but they transmit electric effects are called dielectrics. Dielectrics do not have free electric charges but they get polarized in an electric field, and hence they use it to prevent the leakage of electric charges in electrical engineering devices. The energy gap, that is EG, in case of dielectrics is observed to be very large, of the order of say 10 to the power of 10 to 10 to the power of 20 ohm meter. So this is what about dielectrics. And when we come to the polarization, what is polarization? The displacement of charges takes place in the atoms of a dielectric material under the action of an applied electric field is known as polarization. So this is what the definition of polarization. When an dielectric material is kept under the influence of electric field, so reorientation of charges takes place and the phenomenon is known as polarization. Now I am going to discuss about what are non-polar dielectrics are non-polar molecules and what are polar molecules. So first let us take up non-polar dielectrics or non-polar molecules. Example, oxygen, nitrogen, helium. Okay, so these were all the examples of non-polar dielectrics. If the center of gravity of the positively charged nuclei and the electron cloud coincides, the molecule is called nonpolar molecule or nonpolar dielectric material. For nonpolar molecule, the electric dipole moment is found to be zero. So this is what the observation made. And let us concentrate on what are polar dielectrics or polar molecules. If the center of gravity of the positively charged nuclei and the electron cloud is not coincide, such molecules are called polar molecules. So, for example, water, KCl, and NH3. So, these were all the examples of polar molecules or polar dielectrics. So, if two charges are separated by certain distance, say L, then the electric dipole moment between them is given by mu is equal to QL, where Q is charge of the particle. So this is what the way of finding out the electric dipole moment. So the electric dipole moment for polar molecule is of about 10 to the power of minus 30 coulomb meter. Now I am going to discuss about different polarization mechanisms. There are four mechanisms, that is electronic polarization, ionic polarization, orientation polarization, and space charge polarization. So first let us concentrate on what is electronic polarization. The electronic polarization occurs due to displacement of positive and negative charges in a dielectric material on the application of electric field. So the electronic polarizability is denoted by symbol alpha E. Next, the ionic polarization. When ionic solids such as NaCl are subjected to an external electric field, the adjacent ions of opposite sign undergo displacement. Because of this, net dipole moment comes into picture, and the corresponding ionic polarizability is denoted by symbol alpha I. And the next one is orientation polarization. What is orientation polarization? Orientational polarization occurs in those dielectric materials having molecules with permanent dipole moment. The orientation of these molecules will be random due to the thermal agitation. Under the influence of an applied electric field, each dipole undergo rotation and reorient along the direction of the applied field. The orientation polarization is denoted by symbol alpha naught. And the last one is space charge polarization. What is space charge polarization? When there is an accumulation of charge between two regions comes into picture when a material is placed in an external electric field. So this will occur when two electrodes are connected to a dielectric material. Such a type of polarization is considered as space charge polarization. That is, when there is an accumulation of charges takes place between two regions of a material because of the applied electric field. That is what is called space charge polarization. It is observed that the space charge polarization value is very small when compared to electronic polarization, ionic polarization and orientation polarization. That is why it is not taken into account. Further, the electronic polarizability alpha E is given by epsilon 0 into epsilon r minus 1 divided by n, where n is number of atoms per unit volume of the dielectric material, and the ionic polarization or ionic polarizability alpha I is given by epsilon 0 into epsilon r minus 1 divided by ni, where ni is number of ions per unit volume of the material. And the last one is orientation polarization, that is alpha naught is equal to mu square by 3kt, where mu is permanent dipole moment, k is Boltzmann constant and T is the temperature. The total polarization alpha is equal to alpha E plus alpha I plus alpha naught. So here I am going to explain internal fields in a dielectric material. Internal field is the electric field that occurs at the site of an given atom of solid or liquid dielectric, which is the resultant of the applied field and the field due to all the surrounding dipoles. Let us consider an array of equidistant atomic dipoles. Let D be the distance between neighboring dipoles such that the internal field is the resultant of applied electric field E and the field due to all the dipoles. Now let us consider an atom that is O. The field due to the atoms A1 and A2 is taken into account here, and field due to B1 and B2. First let us consider the field due to A1. The electric field at O due to the atom A1 is given by EA1 is equal to mu cos theta by 2 epsilon dq plus mu sin theta by 4 pi epsilon dq, that is equal to mu by 2 pi epsilon dq as theta is equal to 0. Similarly, the electric field at O due to the another atom A2 is given by A, that is EA2 is equal to mu by 2 pi epsilon dq. Now if you consider both the atoms A1 and A2, the field at O due to A1 and A2 is given by E1, that is equal to mu by 4 the mu by pi epsilon dq. And similarly, field at O due to the atoms B1 and B2 is expressed as E2, that is equal to mu by pi epsilon dq, that is 2d whole cube, that is equal to mu by pi epsilon 2d whole cube. So if you consider all the atoms into account, what happens? The resultant field due to n dipoles is considered as Er, that is equal to E1 plus E2 plus E3 plus E4 plus E5 up to En. So that is equal to mu by pi epsilon dq plus mu by pi epsilon 2d cube plus so on. So after simplification, we are going to get the term that is mu by pi epsilon d cube summation n is equal to 1 to infinity 1 by n cube. So the value of summation of n is equal to 1 to infinity 1 by n cube is approximately equal to 1.2. Therefore, the value of Er is equal to 1.2 mu divided by pi epsilon d cube. Therefore, the internal electric field is given by Ei, which is the sum of the applied field and the field due to all the dipoles. That is, Ei is equal to Ea, that is applied electric field, plus 1.2 mu divided by pi epsilon dq. So finally, Ei can be expressed as Ea plus 1.2 mu divided by pi epsilon dq. This is the expression for internal field at an atom of a dielectric material.